Good morning or good afternoon, depending on what part of the world you're joining us from. But thanks for joining us for this webinar on bipartite projections and the backbone package for R. So I think we'll go ahead and get started as a few more people join the webinar. I'd first like to introduce myself and our presenters. Let's see, hopefully you can see me in video now, but I'm Zachary Neal. I'm an associate professor of psychology at Michigan State University.
Hello, my name is Rachel Domagalski. I am a PhD student in the math department, also at Michigan State University.
And my name is Bruce Sagan. I'm a full professor of mathematics. Also, guess what? At Michigan State University.
Great, thanks. Well, I'm glad Rachel and Bruce can join us. They'll be on standby to present a bit later in the workshop and also to answer any questions as those come in. I'd also like to thank some of our sponsors. So this workshop is made possible by a couple of grants from the National Science Foundation and also from the Social Science Data Analytics program at Michigan State University. So thanks to both of them for making this possible. So just as far as schedule, we've got the workshop split into roughly two parts. In the first half, I'll be providing a broad overview of bipartite projections and backbones. What are they? When are they used? What are some of the pitfalls? I'll then hand it over to Rachel to give an interactive introduction to the R backbone package. This package actually allows us to extract and analyze backbones of bipartite projections. Then with any remaining time that we have left, we can have some open question and answer discussion if you have specific questions about your own work, and you can practice with some of the other data sets that we've provided in the online materials. So just a couple workshop logistics before we get started. Hopefully you've all had a chance to download the workshop materials at zacharyneal.com/backbone. We'll be using those in the second half of the workshop. So the workshop is being recorded, so it will be available for later viewing. I'll post it on the same website as the materials are on right now. So if you miss something, if you'd like to pause, rewind, try some things again, you'll be able to do that online later. So if you have any questions during the workshop, please don't hesitate to ask. Any questions that you have during the workshop, you can ask using the Zoom Q&A function. There should be a Q&A icon somewhere toward the bottom of your screen if you're viewing this in full screen. It'll allow you to send questions. We may be able to answer those questions live as we're going through the workshop, or one of my co-presenters will be able to type an answer to you in the Q&A window, but please ask any questions that you do happen to have. If you have questions after the workshop, again, please don't hesitate to get in touch with us. You can email me at zpneal@msu.edu. You can also get in touch with both me and Rachel on Twitter. So just a couple final notes. If you have any suggestions for the R backbone package, things that you'd like it to do that it doesn't currently do, bugs that you've identified, problems you've run into, please let us know. We're always looking for ways to improve it and release newer versions. And if you happen to publish a paper or post a preprint that uses the R backbone package, we now have cool backbone package decals. So let us know if you've published a paper. We'd love to take a look at it. We'd love to feature it on our website, and we would be happy to send you one of these stickers. So please let us know what you're doing with the backbone package. So we can jump right into it. What is a bipartite network? Well, bipartite network, in different fields, it sometimes goes by different names. Bipartite networks are sometimes also called two-mode networks, sometimes also called affiliation networks. But in general, bipartite networks are characterized by having two types of nodes. So we'll call these two types of nodes agents and artifacts. So the agents are listed in the rows of our matrix, and the artifacts are listed in columns. So we can take a look at an example. This is the example that we'll be working through with Rachel in the second half of the workshop. So this example comes from the US Senate. So for example, In this case, Senators Booker and Warren are listed as rows, and these are the agents in our bipartite network. So in the columns, we have two artifacts in this example. These are both Senate bills. Senate Bill 498, which in this session was the Constitutional Concealed Carry Reciprocity Act, a bill that would allow people to carry concealed weapons. And Senate Bill 862 was the Paycheck Fairness Act. This was an act to reduce gender wage discrimination. So in a bipartite network, the edges can only connect an agent to an artifact. In a bipartite network, edges never exist between two agents or between two artifacts, but only between an agent and an artifact. So in this example, we can use edges to represent senators sponsoring bills. So in this example, Booker and Warren both sponsored Senate Bill 862. And you can see a 1 in Booker's column and 862 column and Booker's row, and likewise for Warren. But neither of them sponsored Senate Bill 498. So we have a 0 in Booker and Warren's rows in the column corresponding to Senate Bill 498. So that's a bipartite network. What we're particularly interested in this workshop are bipartite projections. So a bipartite projection converts a bipartite network into a symmetric one-mode network. And these bipartite projections have a number of unique features. So first, bipartite projections contain nodes that represent the agents. So you'll notice the artifacts at this point have disappeared. The nodes are agents. And so returning to our example, a bipartite projection of that original bipartite data will give us a network among senators. And you can now see, as we would expect in a symmetric one-mode network, our nodes are arrayed as both rows and columns. But in a bipartite projection, the edge weights will tell us the number of shared artifacts between each pair of agents. So in this example, we can see that Booker and Warren sponsored 98 of the same bills. And finally, the diagonal in a bipartite projection will tell us an agent's total number of artifacts. So in this case, from the diagonal, we can see that Booker sponsored a total of 261 bills, and Warren sponsored a total of 291 bills. Now, as is common in symmetric one-mode networks, we're typically not interested in diagonal, and that's certainly the case here. And so we'll treat the diagonal as zeros or as missing. It's simply not relevant for our purposes. What we're really interested in are the edge weights and the extent to which we can interpret those edge weights as a kind of social network. So throughout the workshop, I've kept my comments focused sort of at a conceptual level, introducing us to bipartite networks and projections, and left most of the mathematical details out. If you're interested, the bulk of the mathematics is in the preprint included in the workshop materials, so you can refer there. But simply briefly, if we think of our bipartite network as a matrix called B, we can obtain the bipartite projection P by multiplying B by its transpose. So the mathematics is actually quite simple for converting a bipartite network into a bipartite projection. So where do we see bipartite projections? We actually see them in quite a few different fields, answering a number of different research questions. And across these different fields, the agents and the artifacts often take different forms. So one common place, and certainly something that we'll see quite a bit of in this workshop, is bipartite projections being used to understand politics. So in this case, frequently the agents are politicians or legislators, and the artifacts are bills. So in this context, bipartite projections give us networks in which we identify the extent to which politicians have shared bills. So we also frequently see bipartite projections in geography, where the agents are cities and the artifacts are firms, so that we can look at a city network, frequently a world city network, where cities are connected to the extent that they share firms. We see them in business, frequently where agents are firms and the artifacts are the individuals that sit on their boards of directors. So in the business literature, this is often called an interlocking directorate. We can look at the connections between firms as they share directors. Most recently, we've seen bipartite projections be used in psychology, where the agents are not people at all, but in fact mental illnesses, and they are connected to the extent that they share clinical symptoms. We certainly see it throughout science and bibliometrics, where the agents are authors and they share authorship on papers. And so we see, for instance, examples of co-authorship networks that allow us to understand patterns of scientific collaboration. Bipartite projections have also become quite common in genetics, where these networks look at genes connected through their co-expression. We see them in developmental psychology, where researchers often study children who share their membership in peer groups. We even see some examples in food. This was an interesting paper that looked at the flavor network in which ingredients were connected to the extent that they shared flavor profiles. And we sometimes see them in art. In fact, the Hollywood actor network that was made famous in the Watson-Strogatz paper on small world networks was really a bipartite projection in which the agents were actors, and they were connected to the extent that they shared or co-acted in films. And so recently, this has led some to speculate that bipartite projections are actually everywhere. For instance, this paper makes the claim that every one-mode network can be regarded as a kind of projection of a bipartite network. And so what we see is these bipartite projections being used in quite a broad number of fields. So you might wonder, why would we want to study bipartite projections? And we think there's a specific case where they're particularly useful. And that's a case where you're interested in a one-mode network, but that one-mode network you're interested in is impossible or impractical to measure directly. So where might that happen? Well, we can think of a couple different contexts. So for instance, if we're interested in a one-mode network among politicians, that could be interesting to measure directly because politicians are busy and they might have good reasons to lie or to conceal their true relationships. We might be interested in a one-mode network among children, which can be challenging to measure directly because children don't often participate in surveys. It requires parental permission, various types of informed consent, and so difficult to collect directly. In contexts where we want to study networks among cities, it's often difficult to get the necessary type of economic exchange data, which isn't collected at the level of cities. Scholarly collaboration networks, we certainly can't survey academics. They're busy, they've got lots of other things to do, and there's so many of them. So in all of these contexts, there might be a one-mode network we're interested in studying, but it just wouldn't be possible. Bipartite projections give us one way where we can try and infer the unobserved network we're interested in using data that's somewhat easier to collect. Now, although there might be good reasons to study bipartite projections, there are also good reasons not to study them. And I'll talk about just two briefly. So the first reason we might not want to study bipartite projections is they involve data loss. When we convert our data from a bipartite network to a projection, it tells us how many artifacts two actors share, but it does not tell us which artifacts they share. So we wind up losing a lot of information in the process. We'll talk about how the backbone package aims to recover as much of that information as possible. But techniques already exist to study the original bipartite networks. So for instance, bipartite Siena is available now to study longitudinal bipartite networks. Bipartite Bergam exists for studying cross-sectional bipartite networks, and bipartite versions of centrality now exist. So the implication here is that if for your research question, it's possible to study the original bipartite network and not the bipartite projection, do not study the bipartite projection. It simply contains less information. So the second reason we might not want to study bipartite projections is that bipartite projection allows us to convert any rectangular matrix of data into a square matrix. The problem is that not every square matrix can be interpreted as representing a network. To allow us to interpret a bipartite projection as a network, we also need a theory about why sharing artifacts tells us something about the relationships that exist between actors. So if you do not have a theory about relationships that can be derived from agents or actors sharing artifacts, again, it's unwise to study bipartite projections. Now, in some cases, these theories can be relatively common sense. For instance, when we're thinking about legislators sharing bills, we can certainly tell a very straightforward story about how if two senators have chosen to sponsor the same bills repeatedly with each other, this might provide us some reasons to think they're engaged in some type of relationship, political collaboration. So that's the sort of theory that you need to have to make the leap to bipartite projections. Now, if you're interested in a one-mode network and you have a good theory, now what? Well, there's some problems with projections, and that's what the bulk of this workshop is going to focus on, is overcoming some of those problems. So the first problem is we could study a bipartite projection like a weighted network. The problem is that interpreting what the weights mean is difficult. So returning to our example, we know that Booker and Warren sponsored 98 bills with each other. The challenge is we don't know, is that a lot? Is it not very many? What's the scale? The answer to all these questions, as many in science, it depends. It depends on characteristics of our original bipartite data. Specifically, it depends on two features of the bipartite data. So the first thing it depends on is the row sums. So if we sum across all of the bills sponsored in this session of the Senate, we can see that Booker and Warren each sponsored a lot of bills. So Booker sponsored a total of 261 bills, Warren a total of 291, and they sponsored different numbers of bills. So seeing how many bills they sponsored might lead us to think, well, seeing that they picked the same one 98 times is maybe not all that surprising. Maybe that's not particularly good evidence for a belief that they're collaborating. We can also look at the column sums. So this tells us how many people sponsored any given bill. And so we see here some of the bills they sponsored were pretty unpopular bills. So Senate Bill 862 was only sponsored by 45 senators, mostly Democratic senators. And so we might think, well, although this bill was unpopular, Booker and Warren stuck together on it. And so we might look at this information and say, well, maybe the fact that they picked 98 bills really means something, that they were willing to stick their neck out for the same sets of unpopular bills. So this is where the idea of a network backbone comes in. The backbone of a bipartite projection is a binary, unweighted network that aims to keep the most important edges from the projection. So the goal of a backbone is to help us focus on the real relationships and ignore the meaningless ones, so that we have a way of dealing with the values in a weighted bipartite projection. The challenge, of course, is figuring out how do we decide which edges we're going to keep. So I'll first talk about the easy way, and this is the way that's relatively common in the literature right now. The easy way to decide which edges to keep is we pick some threshold t, and then we keep any edge that's stronger than t. Now, sometimes people will pick a very low value of t, like 0, in which case we keep any edge that's stronger than 0. In our Senate example, that would mean deciding that two senators are collaborating if they sponsored any number of bills together. So you can see this approach might encounter a couple of problems. So the first problem is, how do we pick t? We could pick any value we want. So each value we pick is relatively arbitrary. It's also a challenge because each value we pick will give us a slightly different backbone with a different structure. The second problem is that no matter what value of t we pick, our backbone will always have a couple characteristics. It will always be dense, it will always be clustered, it will always have high transitivity. In short, backbones generated using this approach will always be unhelpful. So what we need is a better way to decide which edges we're going to keep in our backbone. So we can go from a backbone that looks like this, which is not terribly helpful, to a much cleaner backbone that preserves the structure, in this case, of the US Senate polarized into groups of Republicans and Democrats, by using better methods of backbone extraction, that is, better methods of deciding which edges to keep. So methods of backbone extraction let us do a couple things. They let us use a statistical test to decide which edges to keep so that our decisions aren't arbitrary. And they allow us to control for different features in our original bipartite data. So currently we have 3 different approaches to backbone extraction that are implemented in the backbone package and that Rachel will be demonstrating in just a moment. So the first method is called the hypergeometric model. So the hypergeometric model allows us to control exactly for the row sums. So it controls for the fact that Booker and Warren, for instance, sponsored different numbers of bills. This method is very, very fast. The second approach is the stochastic degree sequence model. So this allows us to control for both the row sums and the column sums. The fact that different bills had different numbers of sponsors, that some bills were popular and other bills were unpopular. Now, the stochastic degree sequence model, or SDSM, is unique in that it only approximately controls for these row sums. Now, that approximation is helpful because it makes this approach relatively fast, although it is slower than the hypergeometric model. So the last method that we'll be talking about is the fixed degree sequence model, or FDSM. This allows us to control for the row sums and the column sums and to exactly control for them. So this exact control comes at a cost of speed. This is the slowest model that's currently implemented in the backbone package. Now, each of these different methods gives us a distribution that we can use to test whether a particular edge's weight is statistically significant. And so it gives us a way of deciding whether we should keep an edge in the backbone. So you can see if we had used the hypergeometric model to test this edge between Warren and Booker, it would give us one distribution sort of shifted to the left toward lower numbers. If we use the SDSM, the yellow curve, or the FDSM, the green curve, they would give us, in fact, very similar sorts of results, although notably the SDSM will do this much faster than the FDSM. So once we've used the backbone package to generate these distributions, we can finally ask, we know Booker and Warren sponsored 98 bills together. We can conclude from these distributions that is a statistically significantly greater number of co-sponsorships than we would have expected under one of these random null models. And so we might use this to conclude 98 is a large enough number for us to conclude, at least in the case of Booker and Warren, that they may be collaborators. So that's given a bit of an overview of bipartite networks, what they are, where we might see them, and how we might use them. Now I'd like to turn it over to Rachel to think about how we might actually extract a backbone. And here's where we can switch gears and talk about our backbone.
All right, so hopefully everyone can hear me now. Let me just get this up. Okay, so what we're going to do now is sort of walk through how the backbone R package works, and hopefully by the end of this workshop you'll feel comfortable plugging in your own data and extracting your own backbones. So to start off, hopefully everyone was able to download the materials that are available on Zach's website. One of those is the backbone.r file, and that's what we'll be working off of today. So if you can open up that file, you should end up, if you're using RStudio, with a page that looks like this over on my right. And you'll see, if you're new to RStudio, that there are basically 4 different boxes that you have to look at. The top left one contains the script that we're going to work through, basically the code that we're going to run. Below, you'll have the console. This is where you'll see the commands that have ran through R. In the top right, you have this tab, Environment. This is where you can see different objects that you've created. You can click on them to open them. And in the bottom right, we have our files and our plots. We'll be using our plot tab here to be able to visualize different backbones that we've extracted. All right. So if you're new to R, there's a couple different ways that you can run code. Probably the easiest way is you can highlight with your cursor and then click Run up with this Run button at the top. Another way is you can use different keyboard shortcuts. So on Windows, you can do Control-Enter, and on Mac, I believe it's Command-Enter. This will make your cursor jump a bit, so just be aware of that. Or you could run the entire script. And the way you can do that is you can highlight everything and then click Run. So you're more than welcome to do that if you're following along. And then you can scroll through your console down here at the bottom and see the different outputs that we're going to look at. So I'm going to run things line by line just so that we can sort of step through what each of the functions do. Again, if you have any questions, feel free to use the Q&A in Zoom, and we'll try to get those answered for you. All right, to start out, the first thing we want to do is load this function called visHelper. So we can highlight that and run it. This is just going to help us visualize our different backbones. So again, highlight, press run, or control enter. You'll see it ran here. And then we're going to load our packages. So the first package we need is, of course, Backbone. And then we're also going to use the packages iGraph and Stringer. So just in case you didn't install Backbone in the past week, we actually just released a new mini update. So if you want to reinstall Backbone to get that update, you can delete the little # hashtag before install packages and reinstall Backbone. This will give you Backbone 1.2.1. So if you haven't installed Backbone in the past week, I recommend you do that. I'll show you some of the new features that we have. So let's load these 3 packages and use this line 41 of set seed. This will ensure that we all get the exact same results when we go through our simulations. Okay, so in that data that, or in the files that you downloaded from the website, there should have been a data set, and this is called S114.csv. This is the data that we're going to use, and this is the Senate co-sponsorship network that Zach was talking about. So it has the senators and the bills they sponsored in the 114th session. So if you run lines 46 and 47, it should load in that data, and you'll see it up here in your environment. Now, if this didn't work for you, that could be because you need to set your working directory to where you've saved that file after you downloaded it. In RStudio, it's easy to do that by clicking Session, Set Working Directory, and then Choose Directory. Or if when you downloaded the files, you just double-clicked the backbone.r and that's what opened RStudio, then it should already be set for you. So let's check out what this data is, make sure it makes sense. We can do that by running lines 50 and 51. And then let's take a look down here in the console. So dim Senate tells us the dimensions. We have 100 and 3,589. This tells us we have 100 senators, and there were 3,589 bills. And the data takes this form. We have our senators as our actors for our rows of our matrix, and the bills as the artifacts, and they're represented in the columns of the matrix. So this is a bipartite data set. It's a 0-1 matrix, and we're going to be interested in extracting a backbone of these senators. So let's first project this. Let's see what happens. So if we run line 54, this will give us a projection. Again, you can see it up here in your environment. And if we run 55 through 58, we can take a look at what happened. So after we projected it, we can see the dimension has changed to 100 by 100. And that is because we now have senators by senators. Both our rows and columns are senators. Each entry in this new matrix indicates how many bills were co-sponsored. So for instance, Cantwell and Alexander have co-sponsored 15 bills in the 114th session. And we can extract co-sponsorship by listing the names. So G and then subsetting Booker and Warren, they co-sponsored 98 bills. To contrast with that, Ted Cruz and Bernie Sanders, they only co-sponsored 5 bills in the 114th session. So we can now ask how many bills did they need to co-sponsor together before we can assume they have some sort of positive working relationship. And if they're only sponsoring very few bills together, are we assuming they're maybe avoiding working together? Are they in different parties, things like that. So a new feature of our backbone package that is available in version 1.2.0 and 0.1 is that your input for any of the following functions we're going to talk about can be either an adjacency matrix, a sparse matrix object, it can be a bipartite igraph object, or a bipartite network object, which could be coming from StatNet, or it could be an edge list. So we're hoping this covers most of the objects that everyone's using to do network science in R. If you have any other objects that you think would be helpful for this package to include, please let us know. And if you wanted to use a different type of object, the input will work exactly the same. You would just replace where you see Senate in the script with your different object. You don't need to indicate a different class at all. It'll automatically pick it up. Also, when we use the function backbone extract later in this workshop, you can return a backbone graph that's any one of these classes as well. So we're hoping this will make it a little more user-friendly. You won't have to do the conversions yourself. You can pick which one you want to output. All right, so Zach talked about how universal threshold backbones can cause problems. If we just pick a single value to use as a threshold, we often end up with things that are very dense and don't give us a lot of information. You can do these in the backbone package if you want to see an example of what can happen. And here's how it works. So you can define an upper or lower threshold, and an edge is retained and listed as a 1 in your backbone matrix if it's strictly greater than the upper threshold you pick. It's listed as a -1 if it's strictly lower, and it's a 0 if it's in between. When you use the universal threshold function, you can indicate if you want to you can input either your bipartite data or your projected data. It will give you a binary or unsigned backbone if you only include the upper function, and it'll give you a signed if you include both upper and lower. The threshold values can be numeric or functions, as I'll show you. And then, yeah, bipartite input or not. So let's take a look at how this actually works. So Senate is our data that we want to input. This is the bipartite 114th session. And let's say I just want to keep an edge in my backbone if it's positive, if it's above 0. I do that by writing upper equals 0. And the data I'm inputting is bipartite. So I have bipartite equals true. So let's run lines 62 and 63 and see what happened. So down here in the console, we can see that we have 0s on our diagonal. This is just a subset of the data, and 1s everywhere else. And if we visualize that by running 66 through 74, we end up with this plot. So this is what happens if we keep an edge between two senators if they sponsored at least one bill together. And we end up with basically just this blob. Here we have Republicans indicated as red nodes and Democrats as blue. If an edge goes between a Republican and a Democrat, it's purple. And we can see that this just isn't very informative. We're not really seeing any partisan structure here. So let's take a look at something else we could do. Let's say instead of using just a upper threshold of 0, maybe we want to use a function to figure this out. So we can set our upper threshold as the mean plus the standard deviation, and maybe a lower threshold as the mean minus the standard deviation. And we can run line 78 to compute that. So let's see what happened. If I type in universal BB2 for this new backbone I just computed, let's see what these outputs are to start. So if you press the $, you'll be able to see the two different outputs of the universal function. And you'll see there's backbone and summary. The backbone will give us a matrix output that has an edge of 1 if it was above this upper function, and -1 if the edge weight was below the lower function. And we can see that here. Most of these edges are 0. We have a couple negative edges now. We can also see that the function returned, let me pull that back up, universal backbone 2, this summary object. And this summary object's included in every backbone function. And it gives us a rundown of what method we used and what our data looks like. So we inputted a matrix, we gave it a universal threshold. It took 0 seconds to compute. And here's some info about the row and column sums. Okay, so we've ran the second backbone. We know it now has positive and negative edges. Let's plot the positive edges and see what happened. So if we run lines 81 through 89, we can see a new plot using this different universal threshold. Now we get something that looks like this. Okay, that looks quite a bit better than the previous plot we had that was just this blob, this hairball. But since we're using a universal threshold, we might be losing some information that we don't know about. So for instance, what about these two Democratic nodes here? Maybe they only sponsored a couple bills, a very small amount, but they always sponsored them together. That might indicate to us that we think that they are working together. They have some positive relationship. But since we used a universal threshold, that wasn't captured because the actual number of co-sponsorships they had might have been small, and we used a large threshold value. So this is sort of the thing you want to avoid, because universal thresholds can either leave you with something super dense or just be missing some information, and we're not able to know if we captured that or not. So instead, we're going to use the 3 methods that Zach outlined: hypergeometric, stochastic degree sequence model, and the fixed degree sequence model. So scrolling down, here's how you would use the hypergeometric model. So this will capture the situation where we fix the number of bills that each senator sponsored, and we allow each bill to be sponsored by a varying number of senators. So for instance, with Booker and Warren, they sponsor the exact same number, but we don't really care which bills they did. And then the number of people that sponsor each bill can vary. And we're going to compare our graph, our actual data, to the distribution that's created under the hypergeometric distribution. This is probably the easiest function you can run in the Backbone package. It's also very fast. All you have to do is type hyperg and then input your data. It only has 1 parameter. So let's run this line 93. You'll see down here in your console, it tells you that you're finding the distribution using hypergeometric. And let's take a look at what our outputs are. So if we type in hyperg probs, it's our object, and hit the $, we can see that there's 3 different outputs: positive, negative, and summary. Now positive is going to be a matrix where the ijth entry is equal to the probability of an edge under the hypergeometric distribution having a weight equal to or above the weight we observed in our projection. So you can think about this under a distribution curve. This is the upper tail. Negative is the opposite. So it's the probability of an edge having weight equal to or below what we observed. So this is the lower tail. And summary, again, gives us, just like with universal, a rundown of what our data looks like, which method did we use, and how long did it take to run. So if we look at summary again, we can see that we inputted a matrix, we used the hypergeometric model, and it took 0.03 seconds to run. All right, great. So now we have this object that has 2 matrices and a summary. How do we extract a backbone? And to do that, we use our backbone extract function. So this is the function that you'll use to extract a backbone from each of these three models: hypergeometric, stochastic degree sequence model, and fixed degree sequence model. It has quite a few parameters that'll let you sort of customize your backbone to whatever you'd like. But here's basically what you do. You take the object that you just computed that has those two matrices on the summary and input it as your first parameter. You can then choose from these five other parameters. First, you can choose signed, true or false. Do you want your backbone to have only positive edges or positive and negative? If you want positive and negative, you would add in the parameter signed equals true. We have our alpha value. This is the value of our significance test valued. And it is two-tailed. So if I have an alpha value of 0.01 here, and I have signed regardless of if I have signed equals true or false, in each tail, we'll have 0.005% of our distribution. We can then choose to apply a family-wise error rate correction. This is with the parameter FWER. You have three different options: none, which is the standard, the default. You can apply a Bonferroni test correction or a Holm-Bonferroni test correction. And you would do that by typing in FWER equals, and then type which correction you would like. And then you have the parameter class. This allows you to return a different type of object than, say, the one you plugged in originally. So maybe I started with an adjacency matrix and I want to get back an iGraph object. Then I can write class equals iGraph. And the backbone that's returned to me will be now an iGraph object. And last but not least, this is our new parameter that we've added in the latest version of Backbone. It's called narrative. I'm going to add it in here so we can see what it does. So I turn it on by writing narrative equals true. And what it's going to do is give us sort of an explanation of what we did, an example of how we could write about this in a paper, and give us the citations we need to cite both the backbone package and the model. So let's check out what happens when we run line 94. All right, let's look down here in our console. So we've now created this new object, hyperg_bb. This is our backbone object. And since narrative was equal to true, it printed out suggested manuscript text and citations. Here we get a paragraph that talks about how we could talk about our backbone. You know, we use a significance value of 0.01. We compared it to a null hypergeometric model. And here's the citation to the backbone package and to the hypergeometric model. If we take a look at what this object actually is, hyperg_bb, I'm going to type it in the console here. We can see it's actually a matrix, and it has ones and zeros, where 1 is going to indicate a significant positive edge between two senators, and a 0 indicates no relationship. And we can see that there's no negatives in here, and that's because we didn't add signed equals true when we were extracting the backbone. So if we wanted a signed backbone, we would add in this parameter here. Okay, so what did this actually do to our data, to our backbone? Let's plot this. So we can visualize it by running 97 through 104. And we now end up with this plot. Here we can see we have a lot more partisan structure than we did with the strict universal threshold of just greater than 0 co-sponsorships. We can see that there's a lot of edges between Democrats and a lot of edges between Republicans, and also a significant amount in the middle. But we're starting to see partisan structure. which is what we expect based on what we know about US politics. All right, so what if instead of fixing the number of bills each senator sponsors, what if we let them vary a bit? So the stochastic degree sequence model will compare our observed weighted graph to the distribution where each senator sponsors roughly the same amount of bills and each bill is sponsored by roughly the same amount of people. So how does this model work? The first thing it does is computes probabilities for each cell in our bipartite matrix to be equal to 1. And then it applies a Poisson binomial distribution to the weighted projection. What this means is that you have your choice in how to compute the probabilities. And this is done with the parameter model. Here we're going to use the method that we call polytope, but there's also a ton of different other methods you can use that are built into the Backbone package. For a description of them, you can type $SDSM. This pulls up the documentation for this function, and if you scroll down to model, it tells you all the different ones you can use. So polytope uses a package that's called CVXR. If this method doesn't work on your current computer configuration, you can try Logit. This one's also pretty fast. So let's run lines 108 to see what happens. So we see in our console, this says finding the distribution using the polytope model. And what it's going to do is go through, compute those probabilities, apply the Poisson binomial distribution, and then give us back the exact same objects that we got with the hypergeometric distribution. It'll give us a matrix positive, which tells us the probability of having an edge weight equal to or above what we observed. It'll give us a matrix negative that has the probabilities of getting an edge weight equal to or below what we observed. And it'll give us an output summary, which tells us again our info about our row sums and our column sums, as well as what method we used and how long it took. So this will take usually takes about a minute. Hopefully it goes pretty quick for you as well. And then once we have computed this, we will use backbone extract again to figure out what the actual backbone is. So while this is computing, we can think about more about what this function is doing. If we set an alpha value of, say, 0.1, then each tail would be looking for a probability of 0.05. That means if in our positive matrix, we see a value of 0.04, which is strictly less than 0.05, it's kept as a positive edge. So remember that the backbone extract function is always doing a two-tailed test where we divide this alpha value by 2. Okay, so mine is finished running. I can tell that because I have another arrow here. So let's see what this backbone looks like. We can run lines 109 through 119. I'm going to scroll back over here to my plot. All right, so again, we can see way more political divide present here. Most of the edges are contained within party. And there's fewer bipartisan edges here, fewer edges going between the Republicans and the Democrats. We can compare that by going back to the hypergeometric distribution. It was a lot more dense, there were a lot more edges, and here's what we get with the stochastic degree sequence model. All right, last but not least is the fixed degree sequence model. And we're gonna start this running by, let's run line 123. This is our slowest model. And what it does is it compares the observed values to the distribution where each senator sponsors exactly the same number of bills and each bill is sponsored by the exact same number of people. And the way it does this is it samples this distribution by applying what's called the curveball algorithm to your bipartite graph numerous times. So each time it does this algorithm, it's creating a new bipartite matrix where the row and the column sums are fixed. And it'll create as many matrices as you tell it to with this trials parameter. So you're going to have a better sample of this distribution by having more and more trials. It's basically as accurate as the number of trials you are giving it. So that's why it takes a little bit longer. It has a progress parameter, which helps you keep track of when it's going to be done. We can see in my console, it's sort of counting up in percentage of being done. And then it also has this dyad parameter. And what this does is every time it creates a new matrix, it'll keep track of the projected value for a dyad of your choice. So let's say maybe we want to be able to visualize the distribution for Booker and Warren. Under FDSM, are they sponsoring way more than we would expect or way less? We can tell the FDSM function to do that by putting their names in here. And what it'll do is it'll give us back a list containing each of the projected values in each of those matrices we created. So for 1,000 matrices, what was the weight of their edge in the projection? So we're almost done here. Hopefully yours is running smoothly as well. Once this finishes, we'll again extract a backbone that we can visualize, and we can visualize the distribution of the weights for Booker and Warren. So let's run line 125. This computes our backbone object, which then we can visualize. And lines 128 through 133 will let us visualize the distribution. So this is the expected number of co-sponsorships for Booker and Warren under the FDSM model. So we can see it takes approximately this form. If you are to scroll back up and figure out what they actually sponsored in our data, that was line 57. They actually sponsored 98 bills together. But when we look at this distribution, it looks like the mean's about 60. 98 would be way up here. So this tells us it is significant that they sponsored so many bills together. So we should expect to get a positive edge in the backbone between Booker and Warren. And let's see what that backbone looks like. We can run lines 136 through 143. And here's our fixed degree sequence model backbone. Looks pretty similar to SCSM. We have most of our edges contained between Republicans and then between Democrats. Very few edges going between the two parties, which is basically what we expect since we know Congress right now is very polarized and has been for several years. So these are the three different backbone extraction models that deal with bipartite data that are available in the backbone package. Hopefully the parameters and how to run them makes sense. At this time, you can try to plug in your own data, or we provided a second data set that you can use. The second data set we have is the 96th session of the Senate. So still co-sponsorships, but just from many years earlier. And that should have been downloaded at the same time as you downloaded this file. To use it, to check out what those backbones look like, you just replace the 114 when we loaded the Senate data with a 96, and then you can rerun everything again. And you can compare what those backbones look like to what they looked like in the 114th session. Or you could try out these methods with your own data. Remember, you can input a matrix, an iGraph object, a network object, or an edge list, and see what the backbone package can do to your bipartite data. If you have additional questions on documentation or how to use different functions, you can find these by typing !backbone. And this will pop up with the documentation for this package. It'll give you citations to the papers that describe the different methods. And then if you scroll down to details, you can click each of the functions to figure out how to use them. So for instance, I can click SCSM, and it'll bring me to the SCSM page where I can learn about the different models.